Good evening to all of you, and I really thankful to the Structural Geology and Tectonic group, Professor Santanu Bose and Dhruva Mukhopadhyay, to giving this platform to speak about what I have learned so far, so that what I can going to cherish you through whatever I learned. And also I thank Dr. Pratish for a brief introduction about me. So moving on that.
I think you should present now. Yeah.
Yeah, I think that's the title actually. In fact, I gave to Santanu, I think 2-3 days ago. So basically, if you see the Himalaya, that's earthquake is very common phenomena. Basically, there is a construction, there is a destruction, and again a reconstruction. So that's the thing. Basically, we wanted to understand the earthquake processes in Himalaya. So basically the question is that when will be the future earthquake? If it is so, what would be its magnitude, when and where, and what its magnitudes? So that's the basically the nutshell of this talk actually. Before dwelling on to this problem, basically what we will see that this is what I am now moved recently to Central University. We have a first batch of MSc Geology. We are offering the courses. Yeah, moving on to the talk outline of the talk is I will be talking about the brief background about the evolution of the structural geology with the time, and also a little bit on the Himalayan tectonics, then what is active fault and how the earthquakes forms and the relationship between the active faults and the earthquakes. Then eventually I will be talking about a little bit on the hazards. So on the second part, I will be mostly focusing on the materials and methodology and what all the technologies available, how these different subdisciplines of geology is getting amalgamated into getting into the result. Yeah, that's about the evolution of structural geology in tectonics. When you talk about in the early 1830, basically people started mapping the stratigraphy and geological mapping, and eventually then they wanted to understand that there is a correlations between the surface and subsurface. Then the faulting experiment started by the Willis and Rogers. So slowly it started with the quantification of the geological structures by Chamberlain. That's a mass conservational processes. So then moving on to that by the frictional detachments and fault twist system in 1959. Then slowly in 1980, the structural geology plays a major role in, especially for the oil and mineral explorations, like Price and Boyer and Elliott. They proposed a lot of concept on the thrust tectonics. Then slowly at the same time, we have the strain analysis by the Ramsey and Huber groups. So such kind of milestone has been seen by the structural geology and tectonics. If you take from the early 18th century to all the way to the late 19th century. Now, when you come to the 1990, this active fault or earthquake geology or a paleoseismology started basically soon after the San Francisco 1905 earthquakes. They realized the importance of this kind of studies. So basically the Karisai started working on a big trenches across the fault when the earthquake has produced such kind of fault scarp. In fact, in India, it started in 1999 with our old group. We started working since almost 25 years in Himalayas. So that's basically the evolution of the structural geology. All we know that the structural geology plays a pivotal role in basically, especially in understanding any kind of an earth and surface and subsurfaces processes. So brief, we wanted to understand the Himalayan evolutions. Basically, we have the continent collisions. We know that India got basically broke from Australia and Antarctica and moved at such a long distances, and with a rate of 16 centimeter to almost now it is 5 centimeter per year. Now we could see that this is what the cross section of this Himalayan evolutions, when we have this kind of an Neotethys sea was there, and slowly due to the convergence we got consumed by this convergence, and it is typically now kind of an convergent tectonics, basically archetypal kind of on a continental convergent motion. So basically now if you see that this Indian subcontinent, in fact they are moving at a rate of 38 to 40 millimeters. So that means that Himalaya is growing vertically at the rate of 4 to 5 millimeter per year. So this growth basically takes place during the interseismic state actually, or whenever the earthquake takes place, this Himalaya grow at least 4 to 6 millimeter. Now the point is that how this Himalayas grows, basically, if you see that whether this sub-Himalaya grows at a point of time or a lesser Himalaya grows or higher Himalaya grows. So basically, at least in our understanding that whenever the earthquake forms, basically this earthquake resulting to the growth of the sub-Himalayan wedges. This is what our overall understanding that you will see basically from the field observations. So now we know that because of this movement of the Indian subcontinent, we have the two very great processes called endogenous and exogenous processes. These processes are just nothing but like a nail and finger, basically. They are just like a wife and husbands. So you cannot really decouple their processes, but we can try to understand each of these processes like endogenous and exogenous. But I will be focusing mostly on the active fault, especially on endogenous. Let us understand how this endogenous process creates the active faults. When these two processes get married, then they become the natural hazards. Sometimes tectonic processes give rise to the kind of an earthquake hazards, but when it comes to the tectonic and climate, then it will have a different kind of an hazards. But climate, like surface processes, can give the cloud blast and flash floods and kind of many processes accompanying with the movement failure and the frictional strength, etc. Now, if you look at that overall, the globe of our Earth nature, you can see that everywhere we have the ridges that transform into the different ridges, and eventually that Indian subcontinent is moving because of this combination of the seafloor spreading. It occurs at the rate of 38 to 50 millimeters, so that gives rise to the formation of the Himalayas. So because of these movements, we get bunch of micro seismicity all along the Himalayan arc from west to east, so that you can see that. Now the question is that how often the earthquake comes. So that's very important to understand that earthquake and active fault. So can we forecast this earthquake like people are doing in a climate like automatic weather station? They put that cyclone is moving at this rate, and the Toronto or a kind of a cyclone is going to fall on particular coastal areas. Such kind of inferences, can we make it out? So that's the basically understanding whether this kind of an earthquake can be predicted. Of course, the astrologer and mystic people, they just try to predict the earthquake, just they do like kind of a postmortem kind of talking, they just do. But is there any scientific way to really understand when the future earthquake will going to occur and what magnitude? I don't know, at least by now, but we can still understand if you can have the continuous recording of the small scale earthquakes and active fault studies like what we have been doing, like a paleoseismology. So these are all the some of the methodology to understand or to characterize the earthquakes. So in a way that we are trying to really hunting for prediction of at least in a major earthquake. So that's the motivation of this talk actually. Let us take this elastic rebound theory. This is the first theory. We can very well explain that there is a fault. Basically, this is a road, and this is the fault is just moving perpendicular to the road. Whenever the elastic strain, the material is storing and storing. At one point of time, the material releases its critical limit, then it occurs on an earthquake. So that's the concept we could see. Subsequently, you can see in the San Andreas in San Francisco regions, this fencing got really offsetted. So you can see the beautifully interseismic state, the accumulation of the elastic strain, and slowly under the earthquake, during the earthquake, it's getting releasing the strain. Then after this earthquake, you can see the beautiful uphill facing fault scarp and downhill facing fault scarps. So with this kind of an geomorphic expression, Terrace Riser started looking at the fault scarp all along the San Andreas Fault in sometime in 1970s, and he came up with a very good, beautiful first paper in American Journal of Science that paved the road for the paleoseismology. So basically, if you look at the paleoseismology or earthquake geology, because active tectonics, many geophysics, they generally use. Actually, otherwise the geologists, they say neotectonics. Basically, the active tectonics limited to the some kind of durations, basically. But when you go to the neotectonics, then the time scale it will be expanded in terms of orogeny, basically. That's the main key part, actually. That's why the geophysics confined to only the active tectonics. But I prefer to use the active tectonics basically because whatever the structure we see that fault is getting repeatedly activated during the historical time. So that's why I call it as an active tectonics. So when you see the earthquake geology or the paleoseismology, there are two fault features are very important. One is in a static stress domain, that's on-fault features. Then another paleoseismology is the off-fault features. Now, when you take about this particular domain, it is basically a static stress. Basically, you can able to understand its paleoseismic slip, vertical offset, and its recurrence interval, rupture length and magnitude. Overall, we can understand the fault kinematics, whether in which regime the earthquake is occurred. So such kind of informations can be inferred from the geomorphical expression of the particular fault scarp. Whereas if you talk about the off-faulted features, basically it's a dynamic stress domain. Here you can just have some kind of an understanding of the timing of the Nepal earthquake, that's all. But sometime with a large uncertainty, because these liquefactions can happen in a different set of kind of conditions. So we cannot really rely upon such kind of data. So that's why people always have some kind of on a random saying that that's a paleoseismology means something like that. But it's a real paleoseismology is basically on-fault features, what we have been doing so far. So now the question is that where to see the on-fault features, where to see the off-fault features. For in the on-fault features, generally we can see all along the mountain front on the Piedmont zone. Basically, all we know that the mountain orogeny, the thrust front or a deformation front, migrates towards the foreland. Basically, this is the foreland. So mostly the deformation front is moving towards the south, like a proto-thrust, like a typical subduction zones. So we have to look for the Piedmont zones, such kind of informations, provided if we have the different kind of what kind of an seismotectonic setup exists in that kind of area. That's very important. Especially in the off-faulted features, you can locate the places close to the river bank or wherever the water level is very shallow. And sometimes you get the information from the citizen of that local area whenever the earthquake happens. Like example, in Sirbal camp in Jammu Kashmir, that Kashmir earthquake shook the area near the Jammu. So that's how we collect such kind of information from the citizens. So this is the classical example for the 2005 Kashmir earthquake, how these off-faulted features we can see. We have seen on the Jammu Simbal camp, a lot of sand blows is happening. And that kind of information tells about only we can talk about the timing of this particular event, but we cannot talk about the deterministic parameters of the earthquakes. That's the key point actually I was talking in my previous slides. Now the another aspect is that on-fault appearance of an active fault. This is in a strike slip fault in offset Lettuce Row in El Santo in California. You can see the beautiful offset along this particular strike slip fault having the double side kind of a fault scarp. Now, if you see on the such kind of fault scarp in the basin and range in Dixie Valley, you can see the beautiful fencing is got offsetted with having the normal fault actually. So basically, this oblique normal fault slip component. So you can see that this is the fault. This slide has been this took place, and this fencing has been moved. So it's basically an oblique normal slip fault. So these are all the geomorphic expressions we see on the active fault. Now, if you see especially in Kashmir, Himalaya, where the Kashmir earthquake happened, this is the Neelam Valley. Basically, this is the line of control. This is the Neelam River Valley. Basically, it separates these sides. Now, India, this is the Pakistan occupied Kashmirs. And this is what you can see the beautifully that uplifted terraces. Basically, the base is the active fault. You can see that. So the idea is that each of these terraces, they are at different elevations. Basically, it implies that the fault is active at a different point of time. Hence, this T1 is acquired a larger elevation compared to the T4 or T5. If you look at this, the T3 is the youngest of all this, and T4 and T5. So basically, this, if you see the different elevational differences, we can figure out what is their uplift for this particular Kashmir earthquake, then one can make out. So basically, this is what the typical active fault on faulted features it looks. Now, this is a classical example again in Kashmir earthquake. It's very interesting that all along the active fault, Muzaffarabad or a Tanda fault, sometimes the fault tip line has been reached to the surfaces, but sometimes it does not reach, the tip line does not reach to the surfaces. It remains blind. Basically, this is in a folder scarp. This is another classical examples. Sometime all along the strike of the fault, sometime it emerges to the surfaces. That is known as the emergent fault, or sometime it is remain blind, like Gorkha earthquake, it remained blind, but it is subsurface, it is remained blind. So it is in a non-emergent kind of a front. So, but within the paleoseismology, when you talk about the off-fault features, when we have this kind of a ground secondary fractures, sometimes the secondary fractures and the primary fractures will have a different kind of geomorphological and tectonic as well as the structural setup, especially in case of lateral ground fractures, you will get a series of this kind of a scar with a convex or irregular kind of a strike will be there. So that's the key. Basically, they are the secondary ground fractures. It is nothing to do with the mesoseismal surface rupture zones. Okay, now just have a brief look. Actually, if you look at the magnitude of the earthquake, say 7 or about just 7 or 7.8, the surface rupture for the thrust fault generally happens, because 7.8 Kangra earthquake we don't see at all, but 7.8 in Kashmir earthquake we do see the surface rupture along the active fault we could see. So that means this much energy, you can just have some kind of a brief idea how this much earthquake energy develops with a different scale. That's the important information we should understand from these slides. So basically, if you look at the fault scarf, in any kind of an earthquake, that's the kind of an hypocenter. Then when you project it on the surfaces, it's epicenter. Then it all along the particular fault, it moves basically. Basically, this is the ground surfaces where our houses are located. And if this ground surfaces will be disrupted by the fault scarp basically. So fault scarp is nothing but the tectonic landform. It's coincide or roughly parallel to the fault plane that it has displaced the ground surfaces. So this is what the basically, so what we do in the trenching, basically we make big trenches across the fault scarp. Basically, we are trying to understand the cross section or a thrust transport direction or a dip slip movement we are trying to see on the actually displaced landform, so that we can inform all the kind of deterministic seismic parameters. Basically, you might ask, why do you want to do a trench? Why don't you do it on a river section? Basically, the matter is it should be normal to the strike of the fault. But in the case of a river, most of the information will be gone away. It will be stripped off. It will be removed because of the surfacial processes. So that's why we try to locate the scarp. Wherever the scarp potential exists, we do trenching across that particular kind of fault scarp. So basically, as I told you in the beginning of my slides, where to locate these kind of active faults, basically it's the collisional rendezvous, basically, where the plain and mountain fronts meet. Obviously, that's the place we have to see. When you drive from Delhi all the way to the Haridwar, you can see all of a sudden there is a sudden rise in the topography. Basically, the sudden rise in the topography across the south to north indicate there's obviously a tectonic component is involved. So that's the place we have to see. If you see closely all along this mountain front, what kind of geomorphical observation you can see. That's the slide on the Eastern Himalaya. This is in Nameri, just Siliguri, say, I think it is about 40-50 kilometers. It is the Nameri Tiger Reserves. So you just stand here, you can see the beautiful small baby landform. This is the small landform, it's about 12 meters, and we have the background, we have the Lesser Himalaya, we have the snow peak amount. What is this slide is telling us? Whether this, how this orogeny, how the mountain building process is taking place. Basically, it starts with the plain, then we have the baby mountain, and slowly, we have the Lesser Himalaya and we have the higher Himalaya. So any kind of an orogeny, you start creating a big one, and because of that, it started getting the rotational then this wedge got blocked or get older, then it moves another wedge and slowly build up and build up, and such a kind of a similar fashions. You have a different kind of a topography in Himalaya. We have the sub Himalaya, we have a lesser Himalaya, we have the higher Himalaya. So that's how whole topography can be classified. So basically this is what we see. So like I just quote with past, what's fast is a prologue, that's Shakespeare. So we can understand the earthquake behavior from this kind of the landforms basically. So especially the tectonics and geomorphology, such kind of both subdiscipline is getting amalgamated here. Now if you see the some other area in Himachal Pradesh, same thing is happening. Same thing, that is the Shivalik Hills, that's the bedrock, basically hard rock, and you can see the beautiful fall scarp. And this is the Som Nadi. So basically, the scarp will be parallel to the structural grain of the regional Himalayan strain, or a structural grain of the regional Himalayan strike. And basically, this river is normal to this structural grain. And if you see, this is in Punjab, you can see the beautiful step-like features. Again, there is a plain, and again, there's a beautiful baby mountain, and again, there is a sub-Himalayas. So this is how such kind of terrace kind of steps you can see all along the arc of the Himalaya. So that's the very remarkable take-home point after observing entire Himalayan arc from west to east. So this can be explained by two ways. Either this is the Himalayan arc, you bring the transverse drainage, suppose this is north, this is south, you bring the river all the way normal to that. Okay, but you allow the river to flow axially. This is called axial drainage, this is called transverse drainage. So when you do so, then you can have such kind of different kind of step-like features. But river cannot go up to the up part of the slope. So it has to go on perpendicular to the structural grain of the Himalayas. So that's how whatever this kind of a step-like features, but it is not necessarily this step-like feature is seen entire to 2,500 kilometers. Wherever the preservation potential of the scarp exists, you do see such kind of a scarp. So basically the step-like kind of a scarp features is basically nothing but the base of the active fault. So that's the important. Now, this is what happening on the foothills of the Himalayan arc. Suppose, for example, this is the sub-Himalaya, we have a lesser Himalaya, we have higher Himalaya. So basically, you are seeing whatever you are seeing on this part of this region. Now, let us see on the geophysical evidences, what we learn from the geophysical evidences. That's very important now. So if you see all along the Himalayan arc, you can see the main important aspect is that, as I showed you the first previous slides, the microseismicity. So this is the microseismicity we see all along this, and we have the sudden topographic break, as I explained already. There is a sub-Himalaya, lesser Himalaya, and all of a sudden there is a high peak or a snow peak mountain area. That's the higher Himalaya. That is the sudden topographic break exists, that you can see there is an abnormal incision of the river in Yamuna, Ganga, Tista, all this Loit, all these rivers, you can see the abnormal incision at this particular 3.5 kilometer contour interval. This is the place where the sub-Himalaya, lesser Himalaya, all of a sudden you see the higher point of the Himalayas. So what we try to convey to you is that basically the seismicity is almost confining within the 20 degree to 25 kilometers. Basically you see the seismicity, and also there is a sudden rise on the topographic gradient, and also the GPS horizontal velocity vectors also increases. Now if you look at the further enlarged portion of the Himalayan arc, you can see that seismicity, the GPS rate is almost 32 millimeter per year. Now it comes to 33, and almost it increasing towards the east. That's the general understanding. Now, if you look at the much closer, if you take the cross section across this Himalaya, especially in Uttarakhand, you can see this kind of an configurations. So basically we have the higher Himalaya. This is the sudden topographic break exists. Then we'll have the always it's a sub Himalaya, sorry, lesser Himalaya. Then we have the sub Himalayas. So you can see there is a sudden kind of a topographic break in which most of the microseismicity hypocentral is confined here, and we can see such kind of the zone. If you project it, this is almost somewhat around 20 to 25 kilometer width. You will expect to see such kind of a seismicity on this locking line. So now if you look at this, take the similar cross sections across the Himalaya from south to north. This is the GPS horizontal velocity vectors. Now you can see that this is the India and Nepal cross section. Basically the GPS velocity is increasing, and here the down dip of the decrement is continuously creeping. That's why the velocity vector is keep on increasing more. So basically you can see this particular point, there is a increase in the GPS velocity vectors. So now you can visualize basically in a Himalaya during the interseismic strain. So you can see that this is the locked portion of the particular detachment or Himalayan decollement. You can see that whole of this accretionary wedge is accumulated the elastic strain, and it is giving rise to the microseismicity time to time. And during the co-seismics, it creates some kind of a large to medium-sized earthquakes. It remains in the interland. This is the interland. And some of the great earthquake, what we see in the geomorphical observations all along the Himalayan arc, we just try to see such kind of a false scarp. Basically, it has some kind of an 8 meter of vertical separations we see on all along the mountain front that resulting due to the co-seismic great earthquakes. So if you look at this same kind of cartoon in 3D perspectives, you can see beautifully this is the Endogenous plane. We have the sub-Himalaya, we have a lesser Himalaya, we have the higher Himalaya. So I was talking about this higher Himalaya, base of the higher Himalaya, in which locking line, in which orographic barrier, everything merges basically. So we have the surface observation, subsurface observation, and physiographical observation also, because the monsoonal front intertropic convergence zone does not penetrate into the further north of this higher Himalaya. So it's basically there is a kind of a systematic pattern exists in the natural processes also, but we have to only think and we have to collect such information very closely and carefully. Then we can understand that any kind of a natural process, there is a systematic pattern exists. That's the basically a take home point I wanted to emphasize from this block diagram. So what is the technology basically to quantify this landform or quantify this false scarp basically? So basically this is only we have to do a lot of field works. That's the field is the 90% component, but the field work is basically aided by the high resolution satellite imageries, Palladius and Cartosat. And generally we do this kind of Cartosat image. We try to study the Cartosats with help of all kind of a topographic map, and we just put all this kind of information in the ruggedized laptop and we carry with the field. And sometimes some people they use the GPR before going for the trenches. And also many of us, even we do a lot of drone survey. Basically we wanted to understand the lateral extension of the false scar in highly dense vegetated area. It's very difficult to locate the lateral extent of the fault scarp or a strike of the fault. So we use the drone, and we use mostly real-time kinematic GPS for a large-scale mapping, because the elevation is very important aspect, because we will be talking about the vertical throw, separation, and this kind of parameters, especially for doing the kinematic analysis of the fault. Then we use the robotic total station wherever the sentinel satellite signal is lost, because RTK basically when total station is not useful whenever there's a satellite signal is lost, but RTK is useful whenever the GPS signal is given. Then we always sometimes we use the terrestrial radar. So these are all the technology we can utilize. This is a simple anaglyph image. You can see there is a false scarp right on this. This is the landform. It's uplifted. This is down thrown. Basically, if you are familiar, this is the University of Petroleum Energy Studies located in Dehradun in Doon Valley. Basically, this is a part of my book actually. You can see such kind of images for the entire Uttarakhand Himalaya. Okay, now let's see that evolution of technology basically in terms of doing the survey for the field actually. Generally, in fact, I used almost in 2002, we used the stick line and Abney level method to basically to map them, to prepare the micro topographic area of the particular area. So the stick line is a known stick length. We try to use the azimuth of that slope area, then we do such kind of survey. Then slowly we started doing with real-time kinematic GPS. Then eventually now we haven't started with the LiDAR, but I am hoping to start this LiDAR also to develop this study further. So basically this kind of the survey basically gives the micro topographic map for the deformed terrace surfaces, because in a bedrock, you know that foliated, lineated, or S tectonite or L tectonite, such kind of things you can very well appreciate under the microscope basically. But when you have such kind of landforms which has been uplifted, because it is rigid body upliftment is taking place, sometimes you get the folded terraces also. So in order to map those kind of structures, basically you need to have this kind of high resolution kind of technology is required to map those landforms. Basically how it works, so we just keep the static receiver at one place and we keep moving. When these two tower they talk each other, the resolution will be in centimeter level. When they don't talk each other, then we come to the lab and we try to process it and make the accuracy remain in centimeter accuracy. That's how we work on that. Then we use the drone. So drone basically used for many purposes, all you know that. Then we use the quadrocopter. Basically we use the GoPro digital camera, the stunt people they use. So we use this digital camera on that and we try to fly with help of the remote. And also we use the ground control point. Basically we have to geotag the images. So we use the Articate GPS to geotag that images, and this is what the base station we kept. And we fly every 20 minutes because the battery is limited only for 20 minutes, and we keep flying wherever our target is achieved. So these are all some of the images you will appreciate, because the elevational difference is about 2.6 meters. So we have to locate such kind of a scarp. Basically we use this kind of a technology, and then we just develop the high resolution tectonic geomorphic map, we say, or a geomorphic map. Basically these are all the different terraces T4 and different kind of on a flat area. It has been abruptly truncated. If you see that this elevated terrace is not extending all the way here. If you look at this thing, the river is perpendicular to this trace. This indicate that this landforms has been totally deformed by the fault or kicked off by the fault. So that's called, it's a deformed part of the terraces. You can see the another place where this is what the river is coming all the way from here, and this is the perpendicular to that. This is the Terrace Riser. So these are all some of the internal informations, detailed informations. Now you can see the high resolution DEM. We map this kind of a high resolution active fault map, and we started doing this kind of a topographic map. We try to see the topographic profile, then we could see 2.4 meters. This is in the Mesi in Nepal border. We did some such kind of a trenches last year only. And this is in Emi Basti and close to the Subansari. And we sometimes we use the GPR, try to see what is the geometry exist beneath the subsurfaces, because we dig almost say 6-7 meters. Now you imagine this is the fault. Now how this fault goes, whether it goes something like this or like this. So in order to know its geometry beneath its subsurfaces, we try to do some kind of a GPR survey, but sometimes we are not very much convinced, because we always try to open a big trench and try to see its subsurfaces. But nevertheless, we have to also use this kind of technology so that we can very well appreciate the slip parameters, those things. Okay, now we know the technology, we know the concept. Basically, how do you quantify? If you know that you have mapped the fault scarp, you know this is the fault scarp, this is generated by some kind of an earthquake. So how do you quantify that? The simple concept is that this is the pre-earthquake surfaces, number one. Once this struck by the fault, then this landform get uplifted depending upon the compressional or extensional tectonics. In this case, it's a compressional tectonics. It's a thrust fault. So one side will go up, another side will be down. So this is the base of the fault scarp. So you see that there is a fault scarp. When you do the excavations, you will find such kind of a cross-sectional geometry. So once this is elevated, the surface processes erode the material, and that forms kind of a colluvium. That's the C1. So when you know the age of this unit and this unit, you understand the timing of the movement. Then to bracket that movement, if you take the sample from the C1, that's a colluvium, you can able to say that's the Y. So X earthquake is happened between these two time gap. But the way I explained, it's pretty easy, but it's not so that. Basically, the dating technique, especially in a case of a very short time kind of an ages, it's not very straightforward. Okay, now you assuming that if it is this scarp is uplifted more than once, then you will have a different set of a colluvium. This is what I showed in a different colors. So we use such kind of a geometry, and we make a big trenches. We use the stratigraphy, we use the soil science, we use the sedimentology, we use the structural geology to constrain what we see in the trench exposure. Many places there is a trench party. People invite many of the scientists to see what you see on the trench wall, so that you can make sure that what is seen by everybody. That is the bottom line of that kind of an exercise. So basically, our basic tool is Trackhoe. We generally hire the Trackhoe. It can go for a deeper level. So once we go to the deeper level, we have to depend on the bucket of the Trackhoe to lay the string, and we have to clean the trench wall. All this kind of business is very tricky, because we always keep the trench wall vertical, so that the measurement will not have any kind of an offset basically. So this is the important aspect. We do the trenching. You can see this is the place where the northeast border, basically in the east of the Subansiri River, you can see the same thing plain, and we have the small baby mountain, and followed by the sub-Himalaya, that is a Shoalix. So we dug the trench, and to see the structural observations, and you can see that this is how we bring the big Trackhoe, and we make a big hole on the faulted landform, and we just construct this kind of strings depending upon the dimension of the trenches. We do 1 to 1 meter grid, or sometime 2 into 1, depending upon the dimension of the trenches, basically to document whatever the structures you could see. This is a beautiful top surfaces. You can see there is a doubling of the top unit, and with having a snout on the big thrust on bulldozing on this. So this is also big structures. You can see such kind of information. So this is a very close-up view what we see in the trenches. You can see the beautiful marker horizon got offsetted along the fault, so it produced the fault related fold. You can see beautiful such kind of an up dip portion, the displacement dies, and down dip the displacement increases. Such kind of informations you can see basically from the trench excavation or exposures. So this is another trench. This is again a fault scarp. This is in the, basically it is in the Niglug region. It's I think it's close to Pasikar actually. This is what a beautiful another trench exposure. We can see there is a bluish clay. It is got sheared off basically, and this unit is in a Schwarix, and this unit. So basically this is about 22-meter long structures. It's about 8-meter deep. You can see the closeness, because we make the photo mosaic and try to construct all this log systematically. Then we visualize these things. you may not appreciate some of the structures because it is all confined or condensed into the A4 size. Basically, that's why you will not appreciate much of the structures, and you have to believe on me on this. So this is what the fault actually, when you go especially in northeastern Himalaya, when you dig more than 5 to 6 meters, sometimes 3 meters also, the water oozes out and water comes out depending upon the groundwater table. So that's how, this is how we have to compromise with many things. Okay, now we know that we have studied the scar. Now we have to understand when that fault is particularly moved. So for that matter, we have to choose the best radiometric technique or best chronology we have to choose. So at least for a paleoseismology or earthquake geology, we use the radiocarbon dating, because tree-ring dating is not possible wherever there is a fault scarp. Whether do we have the tree is located on that particular scarp. So such kind of exercise are very, it's not always possible to get such kind of tree ring dating and everything. So we always go for the calibrated radiocarbon, AMS radiocarbon dating, because it has both accuracy and precisions. And this is how the sample located. And sometimes there are some disadvantages in the radiocarbon dating that I'm not going to explain much on that. And there are some fallout isotope dating. Cesium 137 is being used extensively. I think our team is the first in, I think, in the whole world that we use this paleoseismology for a fallout isotope dating. So it was published in Scientific Report in 2017. And also we use the cosmogenic surface exposure dating. But generally we use this dating technique for the long-term million years time scale. We generally use these techniques. And this basically, the idea is that the sun is seeing this particular surfaces. So you have the, during the ablation processes, so the cosmogenic isotopes, basically beryllium, keep on adding. The larger the exposure time, it will have a larger the concentration of the beryllium. So that gives some kind of an ages we utilize for the long-term studies. So that's the cosmogenic datings. And some people, they use the optically stimulated luminescence dating. They use the river-borne sediments. They basically, this technique basically depends upon the, what is the sediment, what is, when did the sediment see the last sunlight, basically. That is the technique it is basically used for date these sediments. Now we know that we studied the scar, we know the timing, we know there is an earthquake happened. Now why we do so? Basically, that's the best example that in Tenali fault, there was a northern pipeline project they developed. So what they did after studying the fault scar and the fault slip characteristics, what they did actually is in a strike slip fault. So they introduced the technology. They know that some few meter of horizontal motion will take place. Then accordingly, they designed the technology to withstand the earthquake of that particular fault. So this is very successful in the Tenali, Alaska earthquake. In magnitude 7.9, the pipeline did not break. That was the contribution from the earthquake geology or a paleoseismology. So basically, active fault studies provide a solution to the geofragile zone, especially in Himalaya. If you look at the places, especially in oil India, they laid a pipe all the way all along the foothills of the Himalayas, starting from the eastern part from Pasigad all the way to the Siliguri. So such kind of exercise can be done. So after studied this active fault almost more than 2 decades, we could develop such kind of a database basically to, for the Uttarakhand regions. That's basically, that's the studies. We could map each of the fault with a different color code. Basically, it says that when this fault moved, that's the, basically that's the idea. We could do such kind of work in the basically this project was conceived by one of previous director, Professor Anil Gupta, and he gave this project, and I started this project with the product of satellite imagery data with this kind of database information. This is the first of its kind basically in India, and also we have come up with a book on this aspect. So basically what I wanted to conclude is that what we see all along the Himalayan arc, we do see about 8 to 10 meter or 12 meter fault scarp all along the Himalayan arc. That says that great earthquake is really, really real. And now, especially in central Himalayan seismic gap between the 1934 and Kangra, Nepal earthquake, already some 10-meter slip is accumulated. It's almost 673 years past. So I'm not threatening, I'm not making the dramatic scenario, but this is how it is, what we could see. Similarly, all along the eastern part also, there are such kind of a false scarp we do see, and we are trying to come up with such kind of a probabilistic hazard kind of a map will come soon. So that's the bottom line, basically. And this is what the population of the Himalaya adjoining regions, you can understand the damages because it's the 2011 data. Basically, what would be the damage scenario if you have such kind of earthquake of more than 8 or 7.8. I think with this, I really thank you all of you for your patience hearing. I'm done now. Thank you.